In this video, we'll discuss adaptive gradient algorithms, such as ADAM. Adaptive gradient algorithms are the go-to optimization method for almost all of deep learning, so it's crucial to get a good understanding of what is behind them. Let's dive right in. Adaptive gradient algorithms. In order to motivate adaptive gradient algorithms, let's consider the following. So we know that the learning rate has to be adapted in order for SGD to converge. And we also know that different dimensions in the neural network actually require different learning rates. There are some dimensions that are really important, and those tend to have really large gradients, and others that have smaller gradients. And the learning rate between the two of these should be different. However, we can't actually introduce a hyperparameter for every dimension that's the learning rate for that particular dimension. So we can't have a learning rate hyperparameter for every parameter in the neural network that we're optimizing. That would be ludicrous. If we have something like 30 million parameters, then we would end up with 30 million hyperparameters that we need to somehow optimize. So rather, what we would like to do is to adapt these learning rates based on the history of the gradient. And basically, you can actually see this as a diagonal preconditioner matrix that we'll use in order to assess how much each of these gradients should be scaled by. And this preconditioner is adaptive to the trajectory and can be seen as very roughly approximating the inverse of the Hessian. So the first adaptive gradient algorithm I'd like to talk about is Adagrad. For this, the update step looks as follows. So the most important part is here we actually take the squared gradient, and here and in the following slides, all operations are element-wise. So for each dimension, for each parameter, we actually take the square of the current gradient and add it to this vector r. So there we accumulate the squared gradients over all our steps, and this is not dampened or anything. We just add to this. So r only keeps growing because, well, the squared gradient is never negative. And then we take this r and divide the learning rate by the square root of this r. So what that does is when a dimension historically has had large gradients, then we divide the learning rate alpha by a large number. And when a dimension has had very small historic gradients, then we divide by a small value. And so that means it puts the current size of the gradient in relation to previous sizes of that gradient. And well, if there's a parameter that always has this really large gradient, then, well, the fact that it has a large gradient right now doesn't really mean so much. And so we should sort of dampen that parameter, well, dampen the updates of that parameter, whereas a parameter that has had very small gradients in the past and now has a large one, well, there we should actually take a larger step. And just one detail that I haven't mentioned so far, this delta in the denominator here is just a small constant to avoid division by 0. So this is the whole Adagrad algorithm. Now, one potential problem of Adagrad is that, well, as I mentioned, this vector r here only ever grows. So the initial gradient, or the gradient in initial steps, has very long-term influences and reduces the learning rate for a given dimension for good. So it's not possible at all anymore to increase the learning rate for a particular dimension. It will only ever decrease. And there are some desirable properties in this for convex optimization, but actually empirically in deep learning, Adagrad sometimes has premature and excessive decreases in the effective learning rate, and it can't ever recover from having reduced the learning rate for a particular dimension too much. And so naturally, there has been a successor algorithm that fixes this problem. Namely, there has been this Rmsprop algorithm that is an improvement on Adagrad that allows the algorithm to forget its history. And it does so by actually replacing the sum of Adagrad by an exponential moving average of the squared gradient, very much like we had an exponential moving average for momentum. So the update step of Rmsprop is very similar to that of Adagrad. In fact, it only differs in this first line, in which the R is now being multiplied by a new hyperparameter rho that's smaller than 1 in order to dampen this R, in order to forget the history. And the current squared gradient is multiplied by 1 minus this rho. And the rest of the algorithm is exactly the same. So the motivation is also the same. Dimensions with historically large gradients now have a learning rate that is smaller. And well, the one new hyperparameter rho that is called the decay rate, this hyperparameter controls how quickly we forget. So if we set this to 0, then basically we forget immediately. And if we set it to 1, then we never forget. And we're very similar to Adagrad. All right, so this is the Rmsprop algorithm. And this is actually already an effective and commonly used optimizer in deep learning. And for some problems, this is actually the best available optimizer. This algorithm can also be combined with momentum. And in fact, that has been done in the Adam algorithm. So the Adam algorithm also has this exponential moving average of the squared gradient. So this is exactly the same treatment as in Rmsprop, but Adam also constructs this exponential moving average of the gradient. So not of the squared gradient, but of the gradient, and stores that in S. So this is something very similar to standard momentum. So you multiply your previous velocity by a hyperparameter smaller than 1, and you add to that your current gradient times, well, 1 minus that hyperparameter. So basically, this S is what we called our velocity before, and this velocity is used down here. Instead of the gradient, we now multiply the learning rate divided by the square root of the historical squared gradient by this momentum-like velocity. So by the exponential moving average of the gradient, something that's also just more stable of a gradient estimate. And another thing that Adam added over previous algorithms is this bias correction. So what do we mean by the term bias here that actually needs to be corrected? This refers to the fact that these vectors S and R are actually initialized to 0, and they take quite a while until they actually catch up to the true values of the average gradient or the average of the squared gradient. So to visualize this, if we have a simple case where this gradient g hat actually remains constant over a series of steps t, then we would like our S, the moving average of the gradient, to catch up as quickly as possible to this g hat. But that is not actually what happens in practice. If we have a standard hyperparameter setting of rho 1 is 0.9, then at step 1, we actually have S1 equals only 0.1 times g hat. At step 2, the S2 is 0.19 times g hat, and so on. So it slowly moves up, and actually never perfectly reaches g hat, but it converges to g hat. Now, it takes quite some steps until it does so, and this difference between S and the G hat, that is what is referred here to as bias. Now, that is what is being corrected by this S hat. So by dividing S by 1 minus rho 1 to the power of t, we actually get that S hat 1 is exactly G hat, and S hat 2 is also G hat, and so on. So it moves this S directly up here, and it just stays here exactly at G hat for the simple case where G hat stays constant. So yeah, this bias is perfectly corrected by this S hat. All right, so this Adam algorithm, just to tell you where the name comes from, it's short for an adaptive estimate of the low order moments. So the low order moments here are the first and second moment, namely the exponential moving average of the gradient and of the squared gradient. And well, Adam does adaptively estimate these characteristics of our gradients and uses them in order to come up with an adaptive learning rate. As I said, it's an extension of Rmsprop with momentum and also with this bias correction. And Adam is actually the default optimizer in very large parts of deep learning. So it's very effective in many cases. It also has some failure modes, but nevertheless, it's the most frequently used one. All right, so one thing I wanted to emphasize is that, well, despite the fact that these adaptive gradient algorithms like Adam actually allow you to have the learning rate controlled adaptively, this does not mean that you don't actually want to explore scheduling the base learning rate. So they are relatively stable with respect to the learning rate, a bit more stable than stochastic gradient descent perhaps, but they still rely on an alpha. So if you look into this algorithm, there's still an alpha in here, and if you choose this alpha too large, then this algorithm will not work. If you choose this alpha too small, then this algorithm will not work. And you actually can also decrease this alpha over time. In Adagrad, the learning rate, the effective learning rate could only ever go down because, well, the R vector there would only grow over time. But in Adam, that is not the case. So the effective learning rate of Adam doesn't actually go down without you doing something to it. And if you want to get better performance, then it is indeed a very good idea to adaptively schedule that. And that is something that is really very rarely done in deep learning. There's this misconception that, well, adaptive learning rate algorithms just take care of the learning rate and you don't need to do anything anymore to help them improve. And that empirically is just not true, as we showed actually just as a tangential finding in this paper of ours that is a follow-up paper to the SGDR paper in which we look at decoupling weight decay. So more about that another time, but I briefly want to tell you about this result that we show in this particular paper, which actually looked at the performance of Adam, so without cosine annealing, but without any type of annealing, just with a fixed base learning rate alpha. And so the plots, how to read these, this is the initial learning rate to be multiplied by 0.1. And so this initial learning rate is just alpha. And here we have the L2 regularization factor. Long story short, we just wanted to explore how strong the algorithm is with different types of regularization and how easy it is to find a good learning rate, a good initial learning rate in this case. And this initial learning rate in this case here is actually just a fixed learning rate, whereas in this case of step drop here, this initial learning rate is, well, just the initialization of step drop. And here, Adam with cosine annealing, also, that's just the initialization of cosine annealing. And it is not the case that these learning rate schedules work better because, well, they reduce the learning rate over time, and with Adam, we actually only use 2 large learning rates or anything like that. No, we actually looked over a large array of different learning rates and found that actually for all of them, well, the Adam with a fixed base learning rate is actually weaker than Adam with a step drop learning rate, and that in turn is weaker than Adam with cosine annealing. So the way to read these plots is brighter is better, and well, you see that this area here is much brighter than this area or than any area here, and so that there could also be parts that different learning rates or different weight decays that could work well. But well, it tends to work well on the left here, but this is already 0, so we can't actually move further that way. And here Adam with cosine annealing gives us quite substantially better results than with a fixed learning rate or with a step drop decay. So this is definitely something that you will want to explore. And this is, so this is implemented in the Adam W paper on decoupled weight decay. All right, so this brings us to the end of this video. And as always, I'd like to leave you with some questions. I encourage you to pause the video here and think about them to activate the material. And this is also the last video of this week, and I'll see you next week. Thank you.